So we begin chapter 10, and if you're looking at the lecture document there, you see this is hypothesis testing with two samples. What we did in chapter 9 was hypothesis testing with one sample. What we're going to do here in chapter 10 is a natural extension of what we saw in chapter 9. So we're going to make things a little bit more complicated, but with all of those concepts from chapter 9, if we start with that foundation, then I hope you find, although chapter 10 is definitely going to be challenging, if you are feeling confident about your chapter 9 hypothesis tests and the three versions, then we can step it up here with what we're going to see when we look at two samples. So let's begin just with some what we see there at the top. So it says claims are often studied using samples from two groups. Maybe the first one there, a company wants to know if their new windshield treatment repels water more effectively than an untreated windshield. 10 untreated windshields were tested by simulating rain. The same 10 windshields were then treated and the experiment performed again. So if you're like me, this one, it reminds me of seeing Rain-X commercials. So Rain-X is this little spray that you put on your windshield, your car windshield, and it's supposed to repel the water really fast. So it makes your visibility in a storm almost perfect, almost identical to if it wasn't raining at all. And I remember in the commercial, right, they like divide a windshield in half, and they treat half of it with Rain-X, and the other half is untested, and they show you, that it's almost impossible to see out of the one in a heavy rainstorm, right, out of the untreated, but the Rain-X side is, perfectly clear. Okay, so that's what's going on. Except they have 10 windshields, they test them untreated, then they put the treatment on them, their product, and then they hit them with rain again. So they do this experiment twice with the same 10 windshields, right? Okay, so that's one example. So your two groups there, like your untreated windshields are one group, and your treated windshields after they put the product on is like the second group, although it's the same 10 windshields. Or maybe the next one, it is speculated that teenagers sleep more than adults on average. And I think we can probably all agree that's maybe more than speculate. To study this, a sample of 16 teens had a mean of 8.9 hours slept per night with a sample standard deviation of 1.2 hours. A sample of 12 adults had a mean of 6.9 hours per night with a sample standard deviation of 0.6 hours. So here we've got the two groups, right? We've got a lot of details there. But you can imagine, one group is the teens and one group is the adults. Notice the groups aren't even the same size. There are 16 teens while there are 12 adults. Turns out that's not going to be a problem. And anyway, all we're trying to do here is like kind of see we've got these two groups. Okay. So what's that sentence underneath? Identifying the relationship of the two groups is the first step for the test with two samples. So it turns out there's a different type of relationship and different problems of the two groups, and that's going to be key to how we go about our test. So it could be that our two groups are independent. Independent groups, the two sample groups are not related, as the outcome of one does not influence the other. So it could be these are two independent groups. Okay, we'll see an example of that in a minute. Or it could be matched pairs. Matched pairs is when subjects in the two sample groups have a natural pairing. So there's a very natural and I feel bold enough to say fairly obvious pairing between the different subjects across the two groups. So you see there in parentheses, often they are actually the same subjects, although we think of them as being in two different groups. So that's kind of strange, but let's go on to practice number one. We're going to begin just identifying Do we have independent groups or do we have matched pairs? So it turns out I have the same two examples that we saw above. Part A, a company wants to know if their new windshield treatment repels water more effectively than an untreated windshield. So 10 windshields were tested by simulating rain. The same 10 windshields were then treated and the experiment performed again. And this would be a lot better if we were all in class together, because I would ask, hey class, do these two groups seem to be independent groups or matched pairs? And keep in mind, it's actually the same 10 windshields. We're just thinking of them as untreated in the first group and then treated with the product in the second group. And perhaps you can see that in part A, these are going to be matched pairs. There is a natural pairing across the two groups, right? So the same windshield, right? So each windshield was tested untreated, and then it was tested treated. So we can see, well, the windshield untreated and the same windshield treated, right? There's the natural pairing between the two groups. Okay. Let's read part B. I wonder what it's going to wind up as. It is speculated that teenagers sleep more than adults on average. To study this, a sample of 16 teens had a mean of 8.9 hours slept per night, with a sample standard deviation 1.2 hours. A sample of 12 adults had a mean of 6.9 hours slept per night, with a sample standard deviation 0.6 hours. Which type of group do we have there? And that's the independent groups. Oh, looks like I had a note there. That's the independent groups in part B. It turns out that the outcome of one does not influence the outcome of the other. However many hours these teens are sleeping per night does not influence the number of hours the adults get. Now, sometimes students in a class, they come back and say, well, don't the teenagers grow up to be adults? Well, yes, but that's not what we have here. We have the teenagers and the adults are different people. So what's going on with the teens does not influence what's going on with the adults. These are two separate groups, and their outcomes are not in any way related. Okay, so we want to get pretty proficient at identifying which type of groups we have, because that's going to influence how we go about our test, and specifically how we set up our null and alternative hypotheses and how we calculate our test statistic. So I thought it'd be a good idea at this point, before we go any further and learn some new formulas, that we just recap the steps for a hypothesis test. So you see the 5 steps there at the bottom of page 1. It's the same 5 steps that we've been using in chapter 9. Now we just have new formulas and that sort of thing. So step number 1 is still to state the null and alternative hypotheses. Step number 2 is to calculate the test statistic. Step number 3, find the p-value. Step number 4, compare the p-value to the significance level. And step number 5, based on that comparison, we will decide to either reject the null hypothesis or we will fail to reject the null hypothesis. Turns out what's really different in this chapter it is the first 2 steps, stating those hypotheses and calculating the test statistic. Everything from there on, find the p-value and on, is going to feel and look exactly the same. Okay, so let's go on to the top of page 2. Here it says the hypothesis test for 2 independent groups. Okay, so let's imagine we've got independent groups. We identify that in the problem. How are we going to go about the test statistic? And just for a moment, right, you notice those 2 massive formulas. They look really intimidating at first, but I think with some practice, we can get comfortable with those. Let me start at the top. We always want to know if there is a difference between the populations being studied. So this test is the same as for one sample, but uses the difference of each measure in its calculation of the test statistic. Okay, so you notice, let's start with that formula on the left for the z-score. So let's say we're finding a z-score. You remember in chapter 9, it was the same formula for the z-score as the central limit theorem, right? X bar minus mu divided by sigma over the square root of n. Well, if you look at the numerator especially, instead of having x bar minus mu, that's been replaced with x bar 1 minus x bar 2 minus mu 1 minus mu 2. So we're finding the differences between our two samples, and then we're putting that into really that same formula that we were using previously. One thing that changes quite a bit is the denominator. Notice we're not just subtracting sigmas and subtracting sample sizes. Actually, what we want to do for that piece is add them. We don't want to take the difference of the standard deviations or the difference of the sample sizes. We actually want to add them together because we have a sample size especially, I think, makes clear, like if you have your sample for the first group and your sample for the second group, we don't want to subtract those. You actually want to add them together to get the total sample across all the information. I won't talk in detail about how we end up with that denominator, right? You see it big square root, then sigma 1 squared over n1 plus sigma 2 squared over n2. I'm just going to ask you to trust me on that. That's the formula. Just accept it. Okay. What if we had a student T style problem? So I've just gone ahead and given you the formula that you see there. It's the same, except sigma is replaced with S because we have sample standard deviations instead of population standard deviations. Okay. So if we're given sample standard deviations in the problem, we know to use the t-score, but it's otherwise identical. And then one note there at the bottom, when using the t-score, take the degrees of freedom to be the smaller of n1 minus 1 and n2 minus 1. So something to be on the lookout for here. When you look at the degrees of freedom for a student T style problem, you have to look at both sample sizes minus 1, and between those you take the smaller, and that's a way of it's kind of like you can never be more accurate than your least accurate piece of data. So the degrees of freedom really influences the calculation of the t-score, and it really talks about like the spread of the data and how accurate it is. Well, you can't be more accurate than your smallest sample size. So we take the smaller sample size minus 1 to be our degrees of freedom. Okay, we're going to see an example of that in just a moment. Actually, right now, we're going to go to practice number 2. And guess what? It's that data with the teenagers and the adults, how much they sleep. So let's take a look. We're going to do the whole thing. I'll go ahead and read it again. It is speculated that teenagers sleep more than adults on average. To study this, a sample of 16 teens had a mean of 8.9 hours slept per night, with a sample standard deviation of 1.2 hours. A sample of 12 adults had a mean of 6.9 hours slept per night, with a sample standard deviation of 0.6 hours. These populations are normally distributed. Okay, that's good to know because we have small sample sizes, right? 16 and 12. So that original data needs to be normally distributed. Then it says with a significance level of alpha equals 0.05. Is there enough evidence that teenagers sleep more than adults on average? Do you think this data can let us statistically prove that teenagers do sleep more than adults? Let's find out. Okay, back to my camera here finally. First thing we want to do is identify which type of groups we're working with. Well, we've already talked about this. We have independent groups. Okay, since we have independent groups, we know we're going to use one of those two formulas for the test statistic that you see above. However, our first step in the test, of course, is to state the null and alternative hypotheses, and that's going to be a little bit different. So let's chat about that. Step number one: state the null and alternative hypotheses. Okay, in order to do that, you can see on the screen there, we need to identify how we're going to call each group. So we need a group 1 and we need a group 2. And I think it makes sense in this problem to say that group 1 is the teens and group 2 is the adults. That could easily be reversed. I pick it this way because the problem talks about the teens first and the adults second. So it makes sense to say group 1 is the teens and group 2 is the adults, and that's really all it's based on. Okay, thinking of group 1 as the teens and group 2 as the adults, how would we represent the null hypothesis? Here's what we would do. Ignore this just for a moment. Focus right here. What are we going to assume to be true? What's the nothing hypothesis? In this case, we're going to assume that teens and adults sleep the same amount each night. Okay, we assume there's no difference between the number of hours the teens get and the number of hours the adults get. So we're going to say H0 is mu1 equals mu2. The average for the teens equals the average for the adults. Okay. What would be the alternative hypothesis? So again, we're going to have mu1 and mu2. Again, ignore this for the moment. I'll cover that up. We're going to have mu1 and mu2. Now, instead of having an equal sign, we're going to either put a greater than or a less than or something there in the middle. Which symbol would fit this problem? And well, they say what we're testing for is, do the teenagers sleep more than the adults? So we need a greater than here, right? We think the teens sleep more on average. Okay. So hopefully that makes sense so far. Thing is, we're never going to express our null and alternative hypotheses quite this way. Instead, here's what we're going to do. Instead of saying H0 is mu1 equals mu2, we're going to say H0 is mu1 minus mu2 equals 0. Think of it as taking a difference. And in the same way, instead of mu1 greater than mu2, think of H1 as mu1 minus mu2 greater than, same symbol, 0. Now you think for a moment, why would we prefer it this way? Well, we're going to see this piece in our formula, right? What we see on that left side appears in our formula, so we much prefer it written this way. This isn't wrong by any means, but we really prefer it this way. And that's the convention amongst statisticians. Okay, so what's the difference when you have two groups and you state your null and alternative hypotheses? Well, instead of like mu equals 0 or a number, and then mu is greater than that number, we're taking a difference, right? Mu1 minus mu2 is 0, and then that equal sign gets replaced by our symbol. Really, very similar. Okay, let's move on to the test statistic. Okay, now here's where we're going to look back to those formulas above. In this case, I hope that you are able to identify we need a t-score here because we are given sample standard deviations. So let's go for it. To figure out all the values we need to plug into that formula, we need to, let's go through this one at a time. We need to identify all the different components. We need x1, x2, we need mu1, mu2, we need s1, we need N1, we need S2, we need N2. Okay, a lot of info we need, but it's all right there in the problem. So if we're thinking of group 1 as the teens, then X bar 1 is the sample average of the teens, and they tell us that the teens had a mean of 8.9. So the sample average for the teens, 8.9. A little bit later, they tell us the adults have a sample average of 6.9. So there's X bar 2 is 6.9. How about S1 and S2? Let's go to that. Well, they tell us that the teens have a sample standard deviation of 1.2 and the adults have a sample standard deviation of 0.6. So far, so good. And what else do they tell us in the problem? They tell us N1 and N2, the sample sizes. The sample size for the teens, 16. The sample size for the adults is 12. And you might think, is that a problem that they're different sizes? No, no problem whatsoever. Doesn't matter if they have different sizes. Now you might be thinking, well, what about mu1 and mu2? They don't tell us those. That's true, they don't tell us mu1 and mu2, but we're still going to be able to plug something in there. Let's go about finding our test statistic here, and you can see, well, I'll just show you all of it. So we're plugging in, we got x1 bar minus x2 bar minus, okay, check this out. What should we plug in for mu1 minus mu2? And it turns out it's simply 0. How can we do that? Well, hey, didn't we assume that mu1 minus mu2 equaled 0? So in the formula, we just plug in a 0 there. And if you're thinking, well, will that be the case every time? When it comes to two independent groups, yes. Mu1 minus mu2 will always be assumed to be 0. We assume they're the same. So a 0 will appear here. And we just need to plug in x1 bar, x2 bar, and then we've got our s1 squared over n1 plus s2 squared over n2, and then the square root of all that. Don't forget to square these. That slips students' minds sometimes. And so there we have it. Now there's a lot going on in this formula, so be careful when you calculate the number there, 5.77. I'm going to do it maybe to the side here. Let's see, I'm going to go parentheses 8.9 minus 6.9, and that's, I don't need to say minus 0, divided by square root 1.2 squared over 16 plus 0.6 squared over 12, close my parentheses, and that should do it. 5.77 when I round it. There's our test statistic for step number 2. Okay. Let me try and keep that on the screen. From here on, it's going to be very familiar. Okay, step number 3 is to find the p-value. So, you're going to use your StatCrunch calculator. We're going for the T calculator here, 5.77. How do we fill this in? It's just the same as in the previous chapter. Do we want a less than or a greater than? Well, if we had a greater than in our alternative hypothesis, then we want a greater than here. Or you may even go with the thinking that if you get a positive t-score, positive number means you want a greater than. Okay. Now, when it comes to the degrees of freedom, right, we spoke about that. What do? Take the smaller sample size. We had a 16 and a 12. So take the 12 and subtract 1. Our degrees of freedom is going to be 11. Always use the smaller sample size if they're different. If they're the same, then you just take 1 less than whatever that number is. Right? Okay. When you do that, the smaller sample size. There you go. When you do that in StatCrunch, you should get 0.00006, at least when you round. So there's our p-value. And we are just about to finish off this problem. Right next is to compare the p-value with your alpha. Well, they said alpha was 0.05, so which is bigger? Clearly, the alpha is bigger. And if you recall, what does that mean for rejecting the null hypothesis or failing to reject? If alpha is bigger, what do? We reject the null hypothesis. In other words, we reject the assumption that teenagers and adults get the same number of hours. Rejected. We have shown that teenagers do in fact sleep more than adults on average. I'll give you the interpretation as well. You might say something like, there is enough evidence that teenagers sleep more than adults on average. Okay. We have done a lot in this first video. Let's stop it here. We got more examples to come.